So the flow of the session is going to be, first we're going to talk about why transformers and the pre-transformer era, transformers era, then the transformer details of the transformers, timeline and evolution. And if we have time, then we'll talk about BERT optimizations, training, efficient and sparse transformers, and multimodal agents and RAG. So first of all, why transformers, right? So initially we started on initially things started on RNNs, or recurrent neural networks. It was initially designed to have a sequential processing, or making sure that it predicts the next thing. So it had a concept of hidden state, where it had to had a small memory where it can think about its past, right? Then so that is why we need a neural network that could be a flexible in terms of how many sequential data it could use, right? So now the thing is, our weights keep changing, right? And in order to make sure that our weights change sequentially according to how many data we are giving it, we have something called a feedback loop. So this is a rolled RNN, and this is the unrolled RNN. And here, if you just look at this diagram here, directly what we can see is that one state is going to another. And this transformation of states makes it so that these hidden states keep the memory of their past self. So if we want to predict something like a stock prediction for the 10th day, right? So for that kind of problems, we need to make sure that we have data till the 9th day, right? However, the issue with this particular algorithm was that it had exploding and vanishing gradients, right? And like, for example, if you don't know about exploding and vanishing gradients, exploding gradients sort of, if you have an input and you have some weight, if the weight is less than 1, so if you would have to multiply this n times, right? That n times will make it so that the gradient will become so small that it is so insignificant that it becomes to 0. That breaks the neural network. That is called vanishing and exploding gradient. Same thing for weight. If weight is more than 1, it will be an exploding gradient, right? So sequentially computation, it's a slow training process, and it has a long-term dependencies. So it has issues with long-term dependency in the sense that it forgets things, and it doesn't have a proper hidden state, right? So this issue was solved by LSTMs, right? LSTMs generally, what they work as is they have something called gates. Though these gates have something, they have predicted something called 2 types of memories, right? So because hidden memory was having issues with the long-term dependencies, so what we had is something called a long-term memory and a short-term memory. This line here, right here, is called the short-term memory, and this line right here is called the long-term memory. Right now, what we are trying to do is we are trying to make sure that we have some long-term memory that we keep in our network, so that it does not forget things that easily, right? So one thing that I really remembered about when I was when I have like studied out all this way before, this was very exciting thing for me. Tan is an activation function that goes from 1 to -1, and sigmoid is an activation function that goes from 0 to 1, right? Sigmoid acts as a percentage of how much memory it wants to keep, while tan acts as a how much, what is the memory that is to be kept. So it generally ranges from -1 to 1, right? Now that is the reason why I have written here percentage long-term memory, because we are keeping only some percentage of long-term memory, and we are trying to add this with a potential long-term memory. That then this short-term memory is also added. This is called the this is from the output gate. The output gate gets the short-term memory, that is the past data that it's want to predict the next token from, and that short-term memory is going to give us an output sequence to the next, whatever next sequence it wants to give. But the issue with LSTM was that it doesn't scale well with very long text. So when we try to do this with text, so this would work on something like stock prediction, or something like, if you want to predict some kind of trend, that kind of things will work with this network. However, it is not parallelizable, which means that we have to still give it a sequential data, right? It cannot take the entire text as a whole, and it cannot run all of it and take the entire context in one go. It has to run it sequentially. That is the issue with LSTM. So, bi LSTMs came in, right? Then bi RNNs came in. And with bi LSTMs, what it does is, both of these things have a word by, right? So what it does is it takes the past and the future context both in one direction, and that context is taken, and two LSTMs are run parallelly. So, and then the whole network is concatenated and flattened. So what we are getting here is context from past and the future. I will take questions if you have any question.
We can take questions at the end.
Yeah, fine. So now let's drop into transformers, which is the main course of this whole session. Architecture overview. Now, what about transformers is really one of the most important things about transformers is that attention. Now, we all know about attention is all you need paper, right? But many of us still might not know what, how it really works, right? There are multi types of attentions, and we like confuse all of it a lot of times. Here, I would like to just look at this diagram, see what you can remember, and let's just move on to this. We'll have to break this step by step, and we'll see what happens next, right? Okay. So first is tokenizer. So you might have used the tick token library. Now the tick token library uses byte pair encoding or tokenizing, which is used by GPT models. Now tokenization is the most important step, where basically what we are doing is we are converting our text to the tokens. We can't have we cannot give the entire text as it is, right? So we have to give tokens. So what we do is we break it down into different tokens, right? Depending upon the tokenizer that we are using. Now, it can be subwords, it can be character level, it can also take punctuations, right? Now, I'll be going through what happens. Now, there are some special tokens, such as this G dot, there is underscore and double stars, right? Double hashes. What happens if these things are all given to tell the LLM that there's a continuation of a sentence, or the continuation of a word, or it's part of a subword, right? Or it's the space before a subword. These type of context needs to be given when we are training an LLM, right? And that is why we try to make sure that we tokenize to the best level possible. So here you can see that there's multiple tokenizer types, right? And then word level tokens, character level tokens, byte pair, byte pair tokens, sentence piece. So there are multiple examples. For each unhappiness is underrated, each word is taken out. Character level, one character is taken, right? Byte pair encoding, we are having most frequent subwords. So we are not taking the entire word as it is, but we are breaking the words into more frequent ones, such as un or ness, something like that, right? Then for the word, we are having, we are making sure we are having these special tokens as well that relate to each other. Then we have a sentence piece, so it breaks down sentences as it is, right? Then we have byte level encoding, like I said, byte level encoding. works on byte sequences, and it keeps these white spaces punctuations intact. That is why GPT uses it, right? Now these are some more special tokens. Now this is all done for training purposes, masking. I'll talk about all this later on. Padding, right? Classification token, separator token. All this will be covered later on, right? Now, word embedding. So what word embedding really is, right? Um, word embedding converts these tokens to numbers, right? These numbers are, because we need to convert it to some number form, right? We can't have it as it is, right? So in order to compute, we have to put this into a vector context. So what these embeddings do now, there are multiple ways of doing this, right? The most important way that people do this is have a pre-trained contextualizer. But what the original paper did was that it used the model itself to get the word embeddings. So this is something you can also do. However, this is not really like recommended nowadays. People use other embedding models to get the word embeddings, which is much more quicker. So yeah. Now, uh, going back to the position encoding. Uh, Next, now we need to have some kind of position information about the words that we are having, right? So write a story, for example. So write is first, is second, and story is third, right? We need to make sure that it captures this one, right being the first word, a being the second one. And to do that, there are multiple ways of doing it. The two most important ones are rope and sinusoidal. Rope is a rotational positional encoder. What it does, it gets the positional information from the rotation in a complex space, which is which you don't have to, right now you don't have to care about, because it is not uh, uh, in the original paper. But I would encourage you to read on it. um, on the sinusoidal part, however, it's more easier to understand. It's absolute, and it's done before the attention, and it encodes the position as vectors and then adds it into the input, where there is no weight learn weights, just an extrapolation. So just giving you an example in this particular diagram. um, let's say we have the first word, right? So here we are having 0, we are having 1, we are having 0, and then we are having 1. So we are having 2 for the first, uh, uh, 2 as the 2 for the first, 1, sorry, 0 1 0 1. We are having that kind of vector for the first word, right? That is the positional encoding for the first word. Similarly for the second word, for the third word. Now, you might ask that they might not be distinct, right? But when we have a very big embedding space, they always tend to become very distinct, because these sinusoidal values are drastically changing on each particular, like, values that they are changing. This whole gap will get wider, and each word will be represented by a different combination of vectors. So therefore, um, this will be a much easier to represent, and it will be more unique than you would think in a smaller context. Now, attention. Now let's get to the main thing. Now, attention, we have three types of attention: self attention, mass attention, and cross attention. Now, self attention. Now, I would like you to just focus on this diagram, and you might have seen this in the transformer paper, I'm sure. Um, this transformer, this is the encoder part of the transformer. This is the decoder part of the transformer, right? Now, what this part of the encoder does is the self attention part. So what it does is it basically gets the semantic representation, or the relationship between, or it learns, sort of learns the text or the language of the text, or you can say if I give it some sort of, I give it a dictionary, or I give it some book, right? I give it an entire corpus of book. It will learn the entire thing by doing a self attention. Now, how does it do that? That is done by a token. It understands the token relationship between the sequences. So typically you have some sort of attention mechanism, which is something like QKT by root dk plus m. So this Q is a query vector, this K is a key vector, and this root dk is a scaling. We are scaling this by the dimension of the key. So this is done to just have a more stable input output. There's no other reason for it. M is for masked. So this is masking is done for later on. You don't have to care about M. We are not going to use M in a self-attention sort of mechanism, right? However, so what we do is later on we multiply this by value, right? So in a self-attention, this Q, this K, and this V, all three of these values are taken, or we are getting this from one what you say encoder, and you don't have to get the K and V values again and again. You get this once, and then you can get the query value for each word, and then that query value is multiplied parallelly with all of these K and V's. So this is much what you can say is it's a parallel. We are parallelizing the process, and that is how LSTMs become redundant, and transformers begin to come in shape. Now, if you look at decoder head, right? Decoder head is having a masked attention. Initially, what we do is, so let's visualize it like this, right? You are giving some text to GPT, right? You're telling it to give some kind of some report. Let's say you want to summarize something. So you're giving it some text, right? So GPT has already learned encoder values. It has already learned everything from whatever the corpus it has been told to learn, right? Whatever the training has been done. Now, you have given it some summarization. For summarization, you have given it some length of corpus, right? Something. Now, whatever you have given, that thing you have to make sure that that context is also taken up. So for that purpose, what it does, it has a masked attention. It does masked attention on each of the values that it is follows. So first it takes, like for example, it takes the, right? That the is taken, and then next value is predicted according to whatever whatever it has learned from your text. So that is why we have to do some mass attention to learn that, to learn the sequential generation of tokens. That is called masked learning or masked language modeling. So this can also be told by something called self-supervised learning. So essentially what it's doing is it's just learning from its own input that we are giving, right? And it's outputting something. So yeah, so it builds a contextual understanding of your text or previous text responses. And then there is something called cross attention. Now the cross attention part, this part is the cross attention part. This part was the mass attention. So decoder, so essentially what you see in GPT does not have an encoder part, right? It only has a decoder part, and the reason being, it only works for the text that you have given it, right? So you might have seen, like, it does very well on the text that you give it, but what happens is, because it has such a large, you could say, parameters, that thing that they learn a lot of context behind each of the mass tension, helps it learn a lot of context. And Hence, the whole decoder part comes into play, right? So when you do cross attention, so cross attention essentially what it does, if you have an encoder decoder sort of a setting, which is something done in the translation type of models. So in translation type of models, it sort of learns the uh, translated words, and then the decoder part translates whatever it wants to translate, right? So how do we improve the semantic representation of the next token? So that is how we do it, by doing a cross attention, right? Now let me give you some more examples. Maybe you might understand from this example. um, so if you look at this, all this is self attention, this is masked attention, and this is cross attention. Now you see that we key and values are yeah, so we are not taking the query value from the uh, self attention part in a decoder encoder situation. We are only taking the query from the uh, masked attention. So what we are trying to do is we are trying to match whatever the context we already learned with the query that we want to achieve. So what it essentially does is it takes whatever it has learned and then it outputs it accordingly. And in a sort of masked state, in where it's a decoder only, right? It only has this thing. So what it does, it learns its own data and then it outputs something, right? Whatever it wants to output. If you give it a summarization task, it will summarize. So if you talk about decoder only, so in a decoder only, we can do stuff like story generation or open-ended text, few shorting, zero shorting. So in that kind of situation, that can only be done if our model is very scalable, if it's big enough, right? For example, we give it a start token and the next token will be the sat. That is the objective of decoder only model. For encoder only model, we have the objective, the cat, then we give a mask token. So what this masking essentially does is it tells or it prompts uh, the network to make sure that it gives that output in place of mask. It gives some sort of output. So for example, the cat mask on mask. So what mask mat, right? So it will give sort of instead of mask, it will give me sat and the. That's the prediction that it's making. So this is for encoder only models. This is only done to make sure that it learns the entire corpus without having to, again and again. It's efficient, more efficient form of learning. For encoder decoder only models, it's good for machine translation or summarization. So for example, if you want to make it do something like this is good, convert this to German, right? So it will do das is gut, right? Then is this toxic, right? If you want to prompt it, is it toxic or not? So you are beautiful. Is this toxic? It's not toxic. It has learned that semantic relationship that beautiful is not toxic. Now, residual connection and layer normalization. Now, this is often, it's often not taken seriously, and it's quite important actually, because residual connections are the reason why the gradient flow is like it's there, right? And a lot of networks are very deep, including this network is just goes on for a lot of blocks, and because of this it loses a lot of values, and that is the reason we have residual connection. We want to make sure that our gradient flows correctly, and therefore we have we add the previous value to the next block. So I like here we had this thing, right? We added this here. This is called residual connection, right? Um, Layer normalization. So normalization, what it does, it essentially stabilizes your activations and prevents exploding and vanishing gradients. I already talked about this, why it happens. But what it does is it basically, so our weights don't become very less and very high. That is the only reason we try to do it. And our gradients also will have the same effect, right? So normalization is quite easy. I think, right? I don't have to say about anything about that, but normalizes it across the whole dimension. And yeah, now there are two types of uh, this sort of residual layer, uh, you know, setting. What happens is essentially, uh, either we have two options, right? Either we do a layer normalization after the residual connection has been made, or we do the neural normalization first and then do the residual connection. So what originally we used to do in the original paper was post normalization, which is for later on we used to normalize. So this was harder for, like, it was like, there was a lot of issues with training. This is what the researchers found. And then there came a new technique, which is called the pre-normalization, which improved the training, and then it made it relatively stable. The loss function was much easier to converge, and that is why we now use pre-normalization. So this is a very important thing, right? So it is used across all or most uh, models. Yeah. Now let's come to multi-head attention. So multi-head attention, as we all know, right? It's the number of heads responsible for contextualizing the heads. So let's say I have something, like I see a sentence in a different way. You see a sentence in a different way, right? You might take that meaning of that sentence in a much different way, and to make that happen, right, we have different heads, right? um, so the relationships between the semantics, the syntaxes, and the references between the nouns we are trying to take is much better covered. Like, for example, let's say it's a very big sentence, like, and the cat and the mat, right? For let's example, so cat and mat will be related, but uh, like mat is, let's say, on the floor, so mat floor is not taken, right? That kind of relationships can be taken more. This is just a very niche example, but when we have bigger sentences, it's harder to get relationships between things. So what these heads essentially do is take relationships between, and they focus on that relationship more than the other relationships, right? And the more number of heads you have, the better your model is going to be. However, this makes the model very hard to train. And originally they proposed 8 heads, but the competition increase as we increase the, obviously I think this is quite, if we have the same thing that we are doing 8 times, it really puts a load on the chip. Now what it essentially has is, I think, what it does, it basically does the same thing, the attention, it does it per head, and in the end it can concatenates all the attention heads and gives it out from a linear head. So that was transformers and whatever the evolution that happened, whatever things that happened before it. Now what happened after it is very important for us. Now let's just give ourselves a second to look at all this. um, so initially we had RNNs, right? LSTMs, by LSTMs, transformers. Slowly we moved to BERT. So BERT still has wide variety of applications. It is used across RAGs, and it is used, I think it's used in almost every company. And um, yeah, so it's very important. Distillation and quantization. Now, this is something you would have to study if you want to run your model. on a very edge device, or sort of you want to run it in a very constrained environment, right? LoRa. So this is, of course, you all know low rank adaptation. This is done. This is done. This is for fine tuning. Uh, this is what you can say. It's a decomposition technique, and it what it does is injects weights into our own model. I'll get to that later on. Uh, Instruction tuning is also something that came up recently, and a lot of companies are getting instruction tuned models. RLHF, DPO, PPOs, we have all heard of it. However, because of the constraint of the environment, I might not be able to give a session on that. And let's see how much we can cover, and we'll move forward. Uh, Multimodality, GGML, GGUF, same thing. The quantization, it has different formats. So it is a library. Essentially, you can use this library for running it on your edge devices. I'll get to that later on as well. MOE, which is, I think we all know, DeepSeek got this on 2024, and we all heard of it, which is mixture of experts. Now, this is also a very important thing to look at. Now we already have agents and agentic memory. So what is next? We all have to see what happens next. But if you see some trend, we are always going back to what we already had. So LSTMs had something called memory. You're trying to have that memory here. So we have always learned from something we already have had. So this is a very important thing to keep in touch with your basics. Now, key innovations that happened, right? So Roberta, Alberta, pre-trained transformers, RAG, scaling laws, fine-tuning, LoRa pre-training, right? So these are very important things. You can go and look at these yourselves, but I'll try to cover whatever I can in this uh, whole session. So BERT optimizations and RAG. Now, BERT is something like we talked about encoder models, right? So encoder model is something that, so think of encoder models like, yeah, like for example, you have an examination, right? Uh, a night before an examination, you're trying to learn the entire thing, right? You're trying to learn the entire thing. So what you do, you pick up the book, you just see whatever gets in your head. So that encoder becomes that thing. It learns whatever it sees, right? And the decoder is you in the morning writing the examination, right? Trying to get whatever it can from whatever the input you have given it, which is the questions, right? So that is a very good analogy. You can look it into that like that. Now, so the BERT is a bidirectional model, and it processes text from left to right and right to left. So it has the encoder segment, and it is trained by the encoder architecture. A lot of companies use it, like Google Docs, Gmail, Smart Compose, all these, like analyzing reviews. We can give it a huge set of corpus, and it will extract data according to our requirements, which is where RAG comes into play. Um, the you Now we use two super. Now it is used. Now we already talked about BERT, right? BERT is something by a masked language modeling. Something also called, yeah. So I missed on this part. Something called next sentence prediction. Now next sentence prediction is also another task like MLM. So masked language modeling is also something we can do, but it's quite inefficient. Similar to next sentence prediction. Next sentence prediction, what it does, it predicts the entire sentence in one go. So, and it sort of tells if that particular sentence B is coming after sentence A or not. So that is a task for you to learn, or for the encoder to learn, right? Now, uh, what it does is that this is not efficient, right? We are trying to give an entire sentence, right? This is not efficient. And the masking of these language is not dynamic. Like I have to, it's very static. Like if it is masked, then it will not change the masking. That is how it's going to be, right? With here comes Roberta. Roberta introduces something called a dynamic masking, where it changes its mask and it can learn multiple context, which is much more efficient than BERT. And Roberta, I think, came like 4 years back, and it's still being used. So it's quite efficient. And the the task, the training task of Roberta is changed from next sentence prediction to full sentences without anything. So instead of trying to relate, right, that whole sentence is being contextualized from the previous sentence, right? Now, like I said, BERT is significantly under-trained model and could be improved, and that is where Roberta came in. Now, there are multiple other BERT models. You can have any corpus. So you can have bio BERT, you can have clinical BERT, you can have medical BERT. All these are taken from different text, clinical text, biomedical text, right? You can have, I don't know, you can have a math BERT, right? So all these to learn your latex languages, right? So all this can be done. And sorry. So how does it compare with GPT? So see, GPT is an auto-regressive model. It has sort of a decoder only, like I said. It has a mask, what do you say, masked self-attention. Now that is different from masked language modeling. Do not, they are both different, right? Masked language modeling is only done for encoders, and masked self-attention is done for GPT type decoder models. So, so something you can look into. I have written this in the slides. I'll share this, right? So yeah. Now, of course, RAG, we all know. I don't have to go through the RAG model architecture, but I've already gone through that. These vector spaces are encoder vector spaces are taken in some database, which can be anything. It can be, we use Pinecone. We can use I don't know. There are many different quadrant, right? These type of databases are being taken up for storing the embeddings of your text. Now we come to the training era, or what happened during the training of these models. So I'm just going to go through all these things. This is not recommended for you to like understand it completely, right? But it is something that I'm trying to give you everything that there already is there to learn. So you can go back to these slides and you can look into these slides later on. And there's something I have captured all the resources. You can look into all of that, and you can just you have something of a homework for yourself, right? So scaling laws quantify how a model performs. It improves predictably as we scale up to 3 components. Now, because GPT was initially GPT was a very small model, so we wanted to, it was not very efficient. So we wanted to do something. We wanted to increase its performance, or some loss, accuracy, this kind of metrics. So what we did is we evaluated on 3 different components, which is model size, dataset size, and compute budgets. And we are trying to see if we can scale up any of these 3 things. Now, Kaplan laws and Chinchilla law, these 3 laws are being mostly followed, and they both have their own arguments, right? I'm not going to go into that, but you can go and look into what has to be increased and what has to be focused on during your training part of your model. Now, fine tuning. So fine tuning is like I said, it's PEFT. Now, PEFT, what PEFT is really is, You can go into look into that. It's a very long paper, and I can't go into this. Of course, you can join the group and we can talk about that later on. But yeah, so what essentially LoRa does is it injects some matrices or some layers where we don't have to change the model weights as it is. So the model weights originally are frozen. We're not changing the model weights. We are just adding something on top of it. Maybe you can think of it in that way. And it reduces the number of trainable parameters, and it makes it so efficient that we can even use CPUs to train some models. May take time, but it can be done. So that is why LoRa was one of the biggest breakthroughs. Then we have instruction tuning. Instruction tuning is something that was introduced like 3 years back, 2 years back. And what many of the companies have taken this, and what instruction tuning really does is it we give it a prompt to write some sort of human written instructions, right? We are trying to give it a prompt. We have a data set and we are making it do some task. So like I said, we did some masking, right? We gave it a mask and then we made it train on a mask modeling, right? Now instead of doing that, let's try to change the prompt. Let's try to change the data set. Let's fine tune in a different way to make it more diverse on different tasks. So what this will do is it will make it so much better for zero shorting or few shorting. Like you give few shorting is, so if you're not familiar, I didn't tell you what few shorting and zero shorting is. Zero shorting is basically you give it some prompt, you want it to do some task, and it gives you the output as desired. In few shorting, you give it some examples, like this is how it has to be with this. I want this format to be like this. You give it 2, 3 examples, and in the third or fourth example, you get the desired output. That is few shorting. Now, that is a very efficient thing to do instead of trying to fetch data. That is why we are trying to do an instruction tuning so that this is more efficient than the training an encoder and having a dependency on an encoder. Now, if you look into efficient transformers, right? There are many efficient transformers. We'll not go into that. That are already on production, but we can go into the methods that occur during development of these models. So what happens is distillation and quantization. These are the most two important methods you have to look forward to. Distillation compresses the large models by training some student model. So what you can say is sort of, so I'm not going to go deep into this, but you can say that we have a huge model, right? We are giving it some data. That data is going to teach smaller model which have much fewer parameters. Now, the distill BERT, tiny BERT, all these things are coming from these type of models, where they have learned the context that we have given it to mimic that teacher model or the architecture of that teacher model. So it mimics that architecture, but it does not have the entire thing, right? Of course, there will be issues with the performance, but um, uh, it's very minute in change. Same with quantization. Quantization converts like high precision weights. So, for example, we have floating point 32 in our weights. Now, floating point 32 is what? 32 bits. Now, this 32 bits is taken down. We change or we sort of cut down the number from having 32 bits to having only integer 8 or integer 4, which is 4 bits or 8 bits. So either we are having one integer or we are having uh, two integers. So this is what we are trying to change it change the precision of the weights, right? If we do this, right, we are each neuron is going to have 2x smaller size if we are converting to floating point 16. We are converting to int 8, which is 8 bits. So from 32 we are getting to 8. That is uh, 4 times smaller. So our model is going to run on 4 times smaller precision. However, now you might think, there might be some performance issues, right? But this performance issues do not persist. Like they are minute. There are minute accuracy losses, but more or less it does the job. It gets the job done, and it saves up memory, and it's excellent on production. So now you want to run all of this on your devices, right? We have ggml, gguf. It's a backend. It's a lightweight backend library for putting this on edge devices, and it's a excellent library if you want to run on any device uh, that uh, that is possible. Of course, it has some format. That format, it takes only GPT format, as far as I know, but it's open source. You guys can look into this. Uh, yeah. So let's go and wrap up to our final architecture, which is mixture of experts. Now, mixture of experts is a feed-forward network. It's sorry. So mixture of experts is like it's a network that is having multiple experts. So this expert thing is basically, now what sparse models are, right? Now you might say what sparse is. The sparse is basically sparse activations. Now what sparse activations do is essentially, you, instead of activating the entire network, you have activated only a few percentage of that network. So for example, if you look at this, we only have 6% of the total parameters used in the forward pass, right? Now, I think like right here, there's an example. A 128 billion parameter model with 64 experts running would cost us the same as the 13 billion. Now, isn't that exciting, right? We have such a big model. It follows the scaling law. It will be a better model, right? But with the experts running, um, it is exactly the same in terms of compute. So why? Because it has that sparse activations, right? Um, Instead of one forward network, so there are some changes with the original transformer. In the original transformer, we only have one feed forward network. All the multi-head attention are running parallelly. Then they're all concatenated to a feed forward. That feed forward is only one in nature. In this particular thing, we have different experts. Each expert is going to have its own feed forward. That feed forward takes the top k experts in the router, whatever the router tells us, it takes the top k experts, and that top k experts are being activated as the. So here we also have something called routing or gating, right? Which is makes it much more efficient, because we don't have to activate the entire network, right? You can see what's different, right? There's a lot of things that are different. Uh, However, I'd like to point out that it's much harder to train because of the routing logic. So you have to, the training code has to be much different from that of what you did in the GPT or transformer based models. So it requires load balancing also. And yeah, so that is one thing to keep in mind, except that mixture of experts have always taken the entire stage. And yeah, now resources. So this is where I have kept all the resources. If you go into these slides, I have entire thing. You want to, whatever you want to read on, it's there. And like, I would, this is a homework for you guys, and I think this would only be better if you go through all this on your own, because in such a small session, I cannot like take the entire thing. So, but that is the reason why I have kept the whole and all the resources that I had and I could find in one particular place. So, yeah, that's about it. I think we can jump for question answer. Okay, so we have 5 minutes. Let's take the questions. Yeah,
You can unmute and ask, Rohan.
Hey, Siddhant.
yeah,
Thank you for the session.
yeah.
So hypothetically, if you have infinite compute, do you think increasing the multi-heads in the transform model will just increase the performance, or will it plateau at some point?
So we like there are multiple there are multiple papers that say that it will plateau at some point.
Okay,
In fact, yeah, and if you have infinite compute, you cannot get the best performance or 100% accuracy. That is something that has been established. I think in some paper I read it, but yeah,
okay, cool. Thank you.
yeah. Um, uh, okay, Partha, right? Yeah,
Yeah, Siddhant, good session. So I have some questions related to the multi-head attention and all of this. So in the paper they have described they have used these that technique, so and so the technique, but uh, why eight they have decided? They told in many other papers, but
uh,
are these just the numbers, or there are rationales behind it that in base transformer, 6 heads won't work, only 8 heads should work at the beginning. If they don't have sine or cos, probably some new activation function will work on this. Why these things came up? Can you give us some rationale behind this?
so you want to know why is there
It's
8 heads and why are there
not
not
only
six or
not
12?
only just 8 heads, but across all of these topics. Uh,
Yeah,
Starting from these basic questions everyone asks: why QKV? Many
yeah.
people explain in their own understanding, own intuition, but why exactly? Why not just only Q and V made this revolution? Why still we need Q, V, and K? Probably if attention, if all you need paper, if they said we need Q, K, V, and P, probably then day after everybody will say that yes, these four matrix we need. But the question is, why not four matrix? Why not two matrix? Why three? Because are they saying this? That's why three. Next question is why eight is the best number here. Then why sine and cos in this case? So can you give us something?
So for the attention head question, so there is no, it's agnostic. The number of heads you want to have, it's agnostic, right? Uh, you do not, that is up to you. If you want to have 64 heads, you can keep it, but that will, it has been shown Sohan has asked, it has been shown it will have the same effect. More or less, it will plateau at some point, but it increases uh, the performance of the model. Now, on the first part of the question, this is a very good question, but I tried to understand why. See, for the it is quite understandable why we have three. It's we do not need four now. Something, but we might need two. There could be something we can have with two, but of course, with four, it's going to increase competition, right? So with Q, so Q is something that we are querying from our data point that we have already. But uh, key and values are what we are getting as part of um, what we already trained on, right? So you're understanding that now. Why do we have K and V both? Now, um, this is an amazing thing to question, but talk of this in terms of percentages. We are trying to have percentage of that V value that we want to keep. So we want to attend, the query wants to attend to the key, but it also wants to fetch some value. So it attends to the key, the query attends to the key, and then it fetches value That is why we need 3 matrices. Now if you have some better thing to do with 2 different matrices, go ahead, like, of course, right? Yeah. So that's my answer. Uh, yeah. So we'll move on with Solema. Yeah.
Okay, thank you for your presentation. My question is, what is your advice in terms of architecture of a transformer or vision transformer in terms of originality in 2025?
Originality. So, okay. So, in the terms of
For example,
originality,
for a research work, for example.
okay, a lot of things can be done actually, because transformer is still used across the board. And like I said, see, Parth asked me a question. He said that why don't we use 2 matrices? Why do we use 3 matrices? So you can go ahead and do 2 matrices. If you get some better attention, of course that will be your that will be the sort of. So something like that then definitely is important still right now. So yeah. Shamima, I think next. Yeah.
We are out of time, so I will have to conclude the session here. But we can continue the question answer session on Discord. Siddhant is on Discord, so he can answer any question you have in the ML Summer School channel or in the NFP channel. Thank you so much, Siddhant, for your time, and thank you so much, everyone, for joining.